right, so let's start class by passing around a sign-in sheet. So I'd like to reward the people who are here for being here. So just pass a sign-in sheet around. That makes sure. I'll add a point or two onto your final exam grade. Yeah, just start one there.
Pretty good.
Yeah, that's good for you, right? So just make sure you put your name on it. All right, so last class we had gotten into this problem with this person who was going to try and get from point A to point C. This was this very large pond, right? It had a 2-mile radius to it, and the person could row a boat across, or she could row part of the way and then walk the rest of the way. And she could walk at a different speed than she could row, right? Y'all remember this setup? Yeah. Okay, so what we had determined was that the time, that we were trying to minimize the amount of time it would take her. So we said, all right, time is going to be the time she rows plus the time she walks. And then we used that formula to convert time. Time is distance over rate. So if we know the distance she rode and divide it by the rate that she rode, then that's equivalent to the time that she rode. And same thing here for walking. And we know the rate that she rode was 2 miles per hour, and the rate that she walked was 4. So really, we just had to come up with the distance that she rows and the distance that she walks. We did the distance that she rows by creating a triangle and just using the cosine function. So that's kind of where we left off, all right? And we were now going to try and figure out what the distance she walks is, and that turns out to be this arc. So what we need to do is figure out the arc length, and I had written out a formula for arc length. The formula for arc length was, if you have r, and this is theta, and this s is the letter that we used in pre-cal. S is equal to r theta, where theta has to be in radians to use this formula. So for us, do we know the radius for this arc? So we have to start from the center of the circle. We know from the center to here and the center to here, right? That's 2 because that's the radius of the pond, lake, whatever, doesn't matter. But do you know what the angle is? Well, this angle right here is theta, isn't it? That's the one we're calling theta, right? Well, these two, this is not necessarily theta, right? These aren't the same. But do you remember the Star Trek little thing I showed y'all last class? We need this again. If you start from the center and you draw out like this to 2 points, and then you pick some point back here, it doesn't matter where it is, and draw like this, then whatever this angle is twice as much. All right? Understand? So imagine, if you will, that I had another point coming out like this and going back like this, then whatever this angle is, right? Whatever this entire angle is, this one would be twice that much. Understand? So if this is theta, then the whole thing would be 2 theta, right? Understand? And that means that this right here would have to be 4 theta, which means from here to here would be 2 theta. Get it? So this is 2 theta. So I have, plugging into this formula right here, my picture looks like this. It's 2, 2, 2 theta, and then that'll be, this is actually the distance that she walks, isn't it? You get that? So what is the total time, or what is the time function? It's distance she rode, which was 4 cosine theta, right? Over the rate that she rode, which was 2, plus the distance that she walks, which we just said is what? according to this formula, it's the radius times the angle. So that should just be 4 theta, right? Four theta over the rate that she walks, which is 4. Which is going to simplify to just be theta. But now what we have is our time. We have a time equation, right? That equation depends on a single variable, and that's the angle theta. So I'm going to now write the time as a function of theta. T of theta is 2 cosine theta plus theta. There's a sign-in sheet going around. Make sure everyone signs that sign-in sheet. That's going to get you an extra point or 2 on the final exam for being here the day before Thanksgiving. All right, so the goal was to find the time function so that we could minimize it, right? Once we have the time function, what's the next step? Not yet. Not constraint. Domain. Domain. What's the domain of this function? So what is the restriction on theta? So think about theta. Theta's, the way that we're looking at this is she's standing on one side of the whatever the hell it is, pond or something. She's looking across the other side. She can row the whole way across, right? Or she can turn a little bit and row across. That'll be a shorter distance, right? But then she has to walk. So what is the restriction on this angle? She can go from here, or so she can aim straight across all the way to where?
Up to 90.
Straight up to 90. Now if she goes straight up to 90 degrees, that means she's not going to row anything. She's walked the whole thing. Does that make sense?
Yeah.
So 0 means she's rowing the whole way. Pi over 2, because we have to use radians, pi over 2 would mean she walks the whole way. Understand the difference? Closed interval. So we're going to be able to do a closed interval method. Now we can do the derivative. And that derivative is pretty straightforward, isn't it? The derivative of t is going to be negative 2 sine theta, right? Okay, and what? Theta is our variable, plus 1. The derivative of theta is 1, because it's like x, right? Derivative of x is 1. All right, now set that to 0. So where is this derivative 0? So negative 2 sine theta plus 1 equals 0. And that's a trig equation. We can move things around. Sine theta is a half, right? Is what we're looking at. And we're only looking between 0 and pi over 2. So where on the unit circle, if we're only looking in the first quadrant, right, 0 to pi over 2, where is sine 1/2? What angle is that?
Sine is your
Y coordinate.
pi over 6.
This is root 3 over 2, 1/2. So it's pi over 6 is where this happens. So the solution to this is theta is pi over 6. And that is our critical number, right?
Yep.
So what I'm going to do now, because this is a closed interval method, I'm just going to take pi over 6. I'm going to take the 2 endpoints and I'm going to plug them into the original time function. So I'm going to go time at 0, time at angle pi over 2, time at angle pi over 6. I'm looking for the minimum, right? The minimum value. All right, what happens if I plug in 0 into this? Cosine of 0 is 1, right? Times 2, so that's 2, and then 0 here, so we get 2, right? 2. And this is time, right? So it's going to take her 2 hours. It's going to take her 2 hours to row across. Does that match with what we thought it would be? It's a 4 miles across, right? She rows at 2 miles per hour. So it should take her 2 hours to go straight across, rowing the whole way. All right, what about pi over 2? That would mean she walks the whole way, right? Well, for time-wise, let's see what that is. Cosine of pi over 2 is 0, so that's gone, plus pi over 2. Pi over 2, which is approximately, on your calculator, 3.14 divided by 2, 1.5, something like that. 1.57. $1.57 hours. Does everyone understand that that means she's not going to go across the water at all? She's going to walk along the edge the whole time? And if she does that, it's going to take her less time than it would have taken her to row across, right? Now what about pi over 6? So what is cosine of pi over 6? Come back over here, root 3 over 2, right? So this is 2 times root 3 over 2 plus what? Theta. Theta is pi over 6, right? The 2's cancel. This is root 3 plus pi over 6. And on your calculator, go ahead and get that as a decimal. And you should get, anybody get that yet? Yeah, about 2.26 hours. So she should just walk around. If she's trying to minimize the amount of time it's going to take her, she should just walk across, don't even get in the boat, right? But if the question was, hey, look, she wants to have a nice, leisurely stroll, if they wanted to know the maximum time, this is the way to do it, right? Does this make sense? Yes?
So, the pi over 2 and the pi over 6, is that the angle she would be rowing from?
Yes. She was going to go from point A over to point C? C. And we called this right here the angle theta. So theta is going to represent the angle at which she's going to point. She's either going to point straight across or she's going to point to some edge of the pond which would be closer to her than this edge would be, or this point would be, right? So that angle is whether, does that make sense? 0 is she's pointing straight across, and then as I start to rotate, she's going to aim for some other point on the beach.
And that calculates the time between rowing and walking.
This function right here, tells you exactly how much time it will take her as a function of theta. If you give me theta, you tell me what angle this is, and this is going to spit out how much time it's going to take her. And then we just found the minimum of that function by doing its derivative and all that. This is a somewhat complicated problem. I mean, it's got a lot of stuff in here that's not very natural in terms of like arc length. You have to go back and remember that formula. That little Star Trek formula that I was talking about, that's something that a lot of people don't know about. So this is just to show you how you could incorporate all sorts of different geometry into a problem, but still be able to find an optimum solution. Okay, the homework for this section on your schedule, I did the homework solution video for this section yesterday, and I did, let me see how many problems were there. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There were 11 optimization problems, and I did, I believe, 9 of them on camera. And then yesterday in my Tuesday, Thursday class, I did 1 of them in class, and I left myself 1 more to do, and I'm going to do that in this class. You will have a quiz on Tuesday. Did I tell you all about that yet? No? Okay.
There's only 8 quizzes in campus.
Yeah, I know. Okay, I'm required in calculus in this class to give you this assessment. Okay, we're going to count it as a quiz grade, but it's an assessment you're going to work, individually, so we're going to treat it like a quiz. And it's an optimization problem. And I will give you a hint that it's very similar, very, very similar to a problem in the homework, but I can't tell you which one. I mean, that would just be giving it away. So make sure, over the holiday, you take some time to review the optimization problems and look at my video solutions, because you're going to have to do the whole thing. It's going to be a word problem. You're going to have to set it all up. The good thing about the quiz is that part of it is multiple choice. So it's like, hey, which of these is the objective function? Like, which of these is your function you're trying to minimize? Which of these is the constraint? And so you can kind of I don't know. It kind of takes you by the hand through the problem. But at the end of it, you have to find out what the optimum solution is. Okay. Monday, sorry. Did I say Tuesday? Yeah, I apologize. Wrong day, wrong class. So that'll be on Monday.
So both this, what we did for homework, and this will be quiz grades?
Yes, that's 2 quiz grades, yes. What's wrong with that?
I thought we were only having 8 quizzes.
No, I only had 8 columns for I can always add more quizzes. If I add another quiz, how many have I dropped? Have I only dropped 1 or 2? I've dropped 2. Yeah, I don't think I'll drop more than 2. But so we'll have 9. Drop the one on Monday? No, I can't do that. Oh yeah, I don't have to count it as a grade. But if I tell you, look, hey, take this assessment, and it's not going to count as a grade, then I may not get your full effort. All right. Okay, we're going to do one more optimization problem, then we're going to move on. All right. So this problem that I'm doing out of your homework is number 19, and I do highly recommend that you watch what I did yesterday on my Tuesday, Thursday class. I did number 23. It's a classic problem in Calculus 1 optimization. All right. The main classic ones are like the farmer who builds these pens and wants to get the most area for his chickens or something like that. And then the one that I did on camera yesterday in my class is pretty classic. So the one we're going to do now, not so much, but it's still a good problem. So here it is. I'm going to write it just the way it appears in the book. Find the dimensions. By the way, this is number 19. Find the dimensions of the rectangle of largest area that can be inscribed into an equilateral triangle. I know this looks bad, but of side L, capital L. If one side of the rectangle lies on the base of the triangle. All right, there it is. So from the word problem, hopefully you see that you want to find the, dimensions of the rectangle of largest area, right? Largest area. This is basically telling you want the maximum area possible, right? You need the maximum area of a rectangle. So I want to find, or I want the maximum area of a rectangle. So I need a so I need an area function, right? So I need an area function. Well, the area of a rectangle is pretty simple, right? Length times width, and we're done. The problem is this rectangle can't just be sitting there doing whatever it wants to do. It must what? It's got to be inscribed into this triangle. Now, what does it mean to be inscribed? It's inside of it, but it's touching the edges of the triangle. And one of the sides of my rectangle lies on the base of this triangle. And this is an equilateral triangle, which means what? All the sides are the same length. How long are they? They did tell us, kind of.
One side.
L is the length of the side. So they're not going to give us a number. They're just going to tell us it's L.
So do we have to assume L is a constant? Or
We have to assume L is a constant in the problem, all right? And then whatever we get as our answer, then we can come in and replace L with 10 or whatever, and we'd have a general answer, basically. So let me draw a picture. We have an equilateral triangle, like this. L, 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 right? That's an equilateral triangle. My rectangle must be inscribed into the triangle. Now, there are different ways you could inscribe a triangle, but they say that one of the base, one side of the rectangle lies on the base of the triangle. So let me first draw a picture of a rectangle that would be inscribed. I could draw something like this. You see that rectangle? See how it like touches the corners there? You see that? That's not a very good picture. But do you see how that all four corners touch the triangle? That's inscribed. But it's got to be a special way. It's got to be so that one of the sides of the rectangle lies on the base of the triangle. So I can't draw it like that, right? So it's got to be flattened out. Yes, it doesn't matter. Doesn't matter which one is the base. But the rectangle I draw has to look like this. Right? That's not the only way I could do it. I could do it like this. Right? Those two rectangles are both inscribed with one of the sides lying on the base. Do you all agree with that? And there's an infinite number of variations between these, right? We could go a little bit wider, but it would have to get shorter. We go, the more narrow it gets, the taller it gets, right? So we're trying to figure out what the dimensions should be so that we get the most area out of this rectangle. Understand the problem? Okay, so let's label some things here. I'm going to take this one out of here. I don't want to work with two of them. Let's just work with one of them. So this is one of those problems where I think it's best if I kind of just guide you through it so it's like you see how to do this the first time, and then from here on out, this is something you can do when you're working with triangles. All right, I'm going to just cut this triangle right down the middle. All right? And I'm going to act like almost like this is the origin, like for an x and y axes. Like that's the origin. That's the point 0, 0. And then I'm going to say the distance from here to here. I'm going to call that x. Now that's not the width of the entire rectangle, is it? That's half of it. And I'm going to call this distance from here to here y. That okay? So the area of that rectangle is what?
The whole rectangle or
The whole rectangle.
2
2 times
times x times
x, y, right? Because if this is x, then from here to here is 2x. So we have 2x times y, that's the area. That's an area equation. I need it to be a function. So I need to replace one of these variables. So that means we have to come up with the constraint. And the constraint is obviously going to come from the triangle itself. But how? It's the hard part. And remember, L is a constant, right? L is a constant. So you are allowed to come up right now with this constraint. And your constraint needs to be an equation that contains x and y. It has to have x and y in it so that you can solve for x and y, right? Or x or y. Once we come over here with our equation with x and y in it, solve for one of them, we'll come back and plug it in here, and then we'll have a function, right?
Yep.
But that equation that we have is going to also have a capital L in it. It's got to, because I don't know what these numbers are. So it's, if capital L is in there, that's okay. So can you look at that and see any sort of geometry that we can use to get an equation that connects x and y together?
Area of the triangle minus the area of the rectangle.
Area of the triangle minus the area of the. That's not a. It's actually not a terrible idea.
And then the smallest area of the triangle would be the biggest area of the rectangle.
But here's the thing. I think what you're suggesting is the area of the triangle minus the area of the rectangle should be an equation, right? I mean, should be a relationship between L and x and y. But what's the area of the triangle minus the area of the rectangle equal to? You don't know, right?
I guess you would want it to be the smallest number, right? Because if the area of the triangle, you know, the difference between the two is the smallest, and that gives you the biggest. Right?
No, I agree. I agree. But what you're creating there is really just going to be another function we're trying to now maximize or minimize. And it's still, we are going to have the same problem of having two variables. All right. So let me try and highlight what you are supposed to see here, okay?
Supposed to see more triangles.
Get my red marker here. Grab the dead marker. Okay, you see that triangle? All right. See this triangle. What can you tell me about those two triangles? They're similar. They're similar. Okay, so if we look at that big triangle, I grab terrible marker there. They both have a right angle here, right? And they both have this angle is the same, right? They share that corner. And that means that this angle and this angle have to be the same. And if all of your angles are the same inside of two triangles, that doesn't mean that they're the same triangle. It just means that they're similar, which means that the ratio of the sides are equal. The ratio of corresponding sides. But do you have any information about the sides of this triangle? What do you know? This is the big one. This is the big triangle. What's this side? L. What's this side? Half of L. This is half of capital L, right? This is the whole L. This is halfway. Okay. What about this triangle? Do you know anything about this triangle? This right here is what? Y. Okay? And this right here, careful here, is what? Half of L. This is half of L, right? Take away x. So if this was 5, right? And this is x, then this distance right here would be 5 minus x. Understand that? So this side right here is half of L, take away x. Are you going to be able to use the similar triangles at this point? Can you do ratio of corresponding sides right now? No, because this triangle, I have these two sides, right? And on this triangle, I have those two sides. So I'm going to need to have, if I'm going to have this side and this side here, I'm going to need to have this side and this side here. Or, well, I guess that's the only way I can do it right now. I mean, I could go get this side too, and then do these two and these two, right? But I think this side's easier to figure out. Let's call this right here h. That's the height of this thing, isn't it? And by Pythagorean, what do you know on this one? A squared plus b squared is c squared. So I could write h squared plus 1/2 L squared must equal L squared. That's my Pythagorean on this. By the way, right now I'm not actually getting the constraint. I'm trying to finish off the triangles so I can get my constraint equation. But I need this side before I can do it. So let's solve this for h. If we square, when you square 1/2 L, you get 1/4 L squared equals L squared. So what happens if you subtract 1/4 L squared on both sides? What happens if you take 1 L squared here and take away 1/4? 3/4 or 3/4 L squared. So h squared is 3/4 L squared. And then to find h, I take the square root. So when I take the square root here, I'm supposed to do plus or minus, but I'm going to throw out the negative because h is going to be the height of this triangle, can't be negative. And I just take the square root of this. So that's going to be the root of 3 over 2L. Just taking the square root of each piece. Square root of 3 is root 3, square root of 4 is 2, square root of L squared is L. All right? So now back over here to this picture. This is really root 3 over 2L. Questions? I'm ready for my constraint. My constraint equation is going to need to involve x and y and probably L. So I can set up my ratio however I want. I can go this side divided by this side equals this side divided by this side. Or I can go this over this is equal to this over this. Or I can go this over this is equal to this over this. It does not matter which way I do it. I'm going to choose to do this over this equals this over this. And the reason I'm doing that is because if I do this over this, the L's are gone, aren't they? Okay, so I'm going to write root 3 over 2 L over 1/2 L must equal what? You have to get it in the right order here. This over this must equal y over 1/2 L minus x. And let's start cleaning this up. Do we have an equation that has x and y related in there?
Yes.
Yes? There's an L in there, but who cares? Well, actually, the L, no, we'll still have an L. Here's an L. This L is going to go away, right? And what's root 3 over 2 over 1/2? So flip, just root 3. Just root 3. So this side's root 3 equals y over 1/2 L minus x. Let's solve for y. If I solve for y, I just clear the fraction out, right? I multiply both sides of this fraction by 1/2 L minus x. Just multiply this on this side and on this side. It'll cancel over here. It'll appear over there, right? So you get this, root 3, 1/2 L minus x equals y. You follow? That's the constraint right there. This is your constraint equation, but I've solved it for y. And now I can take that and I can plug it back in over here to my area equation for replacing this y with that. Do you have any questions? All right? The problem that I do on video that I suggest you go back and watch is even more complicated than this. It's a sphere, three-dimensional sphere, with the radius fixed at capital R, and you're inscribing into this a right cylinder. And you're trying to find the maximum volume of that cylinder. And there's a step within this problem that you need to see. All right, so make sure you do watch that. Yeah, you cut it in half. No, you cut this in half and you look at it like a cross section. And if you look at the cross section of that, it looks like a circle with a rectangle in it. And then you can start creating some relationships with things and start using the radius of the sphere. And then, anyway, watch the video. All right. All right, so now at this point, I'm going to rewrite my area. It should now be a function of x. It's going to be 2x times all of that, root 3 parentheses 1/2 L, 1/2 L minus x. Y'all agree with that? Let's go a little bit further. Let's distribute through. Let's distribute this through. So if I multiply this and distribute that here and here, what do we get here? First one, the 2's cancel, don't they? And I just get root 3 x times L. Yes? I'm going to write Lx because L is a constant. What's the last term going to be? Minus 2 root 3 x squared. Two times root 3 x times negative x squared. This is our area function. Questions? Hey, this is just a quadratic, isn't it? That's all this is a quadratic? Root 3L and that's just numbers, right? So what's next? Domain. Okay. What are the restrictions on x? Careful, on x. So go back to your picture, equilateral triangle, rectangle in here. We cut that in half. We called x the distance from here to here, didn't we? So what's the smallest x could be? 0. What's the biggest x could be? To the edge of the triangle, which is half of L, right? It could go from 0 to half of L. Not L, because remember, L is the whole way across. X is the measurement from the center here out. So our domain here is 0 to 1/2 L. Closed interval. Derivative time? Remember, L is a constant, right? L is a constant. So what is the derivative of that function? Constant. Derivative of this times x is just root 3L. Okay. Here, 2 comes out. This is all a constant. So 2 comes out. So minus 4 root 3 x. That's it. Set that to 0. And when you set this to 0, you get root 3L equals 4 root 3x. I just moved this to the other side. And I'm going to divide both sides by 4 root 3. So root 3 over L over 4 root 3 equals x. The root 3's cancel, and you get L over 4. L over 4 is 1/4 L, right? That's our critical number. Now what? Yep. Plugged in where? Original. So I'm going to find the area. Oh wait, they just wanted the dimensions, right? Well, is it obvious what's going to happen when I plug in 0? What's going to happen if I plug in 0? If I plug 0, I can plug it into here or here, right? These are both the area functions, aren't they? If I plug in 0 right here for x, what happens? 0, okay, so that's easy. What happens if I plug in 1/2 L? Plug it into this one instead. What happens if I plug in 1/2 L right here? 1/2 L minus 1/2 L? 0, so that's going to 0 out also. And then what if I plug in 1/4 L? Well, I can tell you this, it's not 0, right? It's some number. I could figure out what it is, right? I could do that. But it's definitely going to be my maximum. Shall we? I'll put it in here. What would we get if we did root 3L times 1/4 L minus 2 root 3 times 1/4 L squared. So I'm just plugging that into this area function. These are together. They're not. Know what I'm saying? The L's on top, not on the bottom. So that's going to be root 3 over 4 L squared. And this one over here minus, let's see what happens when you square the 1/4. 1/16? So 1/16 L squared. So you get root 3 over 4 L squared minus this 2 becomes 1, that becomes an 8. So I'm thinking you're getting root 3 over 8 L squared. It didn't ask us for the maximum area, did it? I'm actually going and answering more than they asked here. Can we get a common denominator between these two? Make that an 8 by multiplying top and bottom by 2. So if I make this a 2, I can turn that into an 8. Then I have 2 root 3 L squareds minus just 1 root 3 L squared, which should just leave me one of them. So I have root 3 over 8 L squared. That's definitely bigger than 0, right? So we have a maximum there. I have not answered the question. The question was, what are the dimensions? So far, we know part of it, right? We wanted the dimensions of this rectangle, right? So what is this side going to be?
So basically 1/2.
It's 2 of these, right? Because remember, x was the distance halfway. So it's 2 of these. 2 of those 1/2 L. So this should be 1/2 L. And what should the height of this be? What should y be? And where are you going to get that from?
You're going to plug that back into your constraint.
Constraint. We had a constraint equation earlier. It was solved for y. We had y was equal to root 3, and then it was 1/2 L minus x. Was that it? When we solved for y earlier?
Yep.
Yeah. So take this x and plug that in. So you get y is equal to root 3. 1/2 L, take away 1/4 L. Isn't that just 1/2 minus a fourth is a fourth? So you get a fourth here. So y is equal to root 3 times 1/4 L, which is just root 3 over 4 L. That's how long this side should be. All right, that's it for optimization. Any comments or anything? Practice. Practice. All right. Where's that sign-in sheet? Did it get around to everybody? Anybody else need to sign this? Here, I'll take that. Thank you. Today is the 23rd. I said I was going to take off 2 points. Is that what I was saying?
Yep.
Okay. We are going to do the last section of of chapter 4, which is 4.7, which is called antiderivatives. All right, so what we're doing here is we're actually beginning Cal 2 a little bit. And it's always good if there's some overlap. Although, I'll tell you what right now, if you look at the course description for Cal 1, this is part of Cal 1, right? This is the beginning parts of antiderivatives is in Cal 1. So there is a goal here. We want to get to a certain place. Now, when you take Cal 2, most likely your instructor will start out with this as a review, so that there's some overlap. All right, so let's talk about this. Let's say that I have some function here, and I tell you that its derivative is 2x. Can you tell me what f was? X squared. Everyone agree? If I tell you the derivative of some function is this, then that means that the original function f of x must have been x squared. Is that the only thing it could have been?
Probably not, no.
There's some other possibilities.
Well, it could have been x squared minus any constant.
Okay, so it could have been this, or it could have been x squared plus 5 would have worked, right? It could have been minus 5, so plus or minus 5 would have worked. But I could have done any number out here, right? Anything. I wanted anything. So what we're going to do instead of this, in trying, you can't list out all the possibilities, is that we'll just say, well, this right here is good enough. This covers all of the possibilities. This right here is a constant. So if you take x squared and add any constant you want to it, and the constant could be a negative number, which would make this subtraction, all right? But as long as that's a constant, a fixed number, then if I take the derivative of this, I'm going to get 2x, right? Derivative of the constant will go to 0. So there's actually an infinite number of answers to this, aren't there? There's an infinite number of answers, but they all have the same characteristics. They're all, in this case, parabolas, right? That have just been moved up or down. So if you take a look at this as a family of functions, here's x squared plus 0, right? X squared plus 1 would be this one, right? X squared minus 1 would be this one. And if you take all the different combinations, right, you create this entire family of functions. Any one of those is going to give you that as a derivative. And geometrically what that means is that if I were to go and pick a point here, x, and go up to the point that's on any one of these parabolas, what are they all going to have in common at that point? Same slope. The tangent line, the slope of tangent line here, all those slopes will be parallel, right? On any of those. Now in the lecture notes for this section, I show you that. Let me see here. That's not a good example. This one's a good example. Okay, so this is a different example, but this red function here, this parabola, is the derivative one. The antiderivative, which is the function it came from, is any one of these black cubic functions. And if you look at all these black cubic functions at the same x value, they all have the same tangent, same slope. So what I want to do for the rest of today is just get us familiar with this backwards process of looking at something and going backwards to where it came from. Thus the word antiderivative, right? It's the opposite of the derivative. Let me give you another one. How about this? How about if I tell you that the derivative of something is x cubed? Can you tell me where that came from? What is the little f? What is little f here?
Has to be like 1/3 x squared, or x to the, or 1/4 x to the 4th.
Okay, yes. Let's think about this. What can you tell me about the power? This is x cubed.
One less than 1.
That's one less. The power came down, right? When you took the derivative, the power came down. That means the power on this one must be one higher than that one, which would be x to the 4th. Agreed? But if I just say it's this and I take the derivative, the 4 is going to come out, right? That does not have a 4 in front. I don't want that to happen. I want it to be a 1 in front, don't I? So how can I kind of get rid of the 4 that's going to come out? Put a fraction in front of this of 1/4. And that will eliminate that 4 when it, well, not eliminate, it'll turn it into a 1. You understand that? Plus a constant. That would be the solution to that. So if you wrote down f of x equals 1/4 x to the 4th plus 5, this right here is an antiderivative of x cubed, all right? This one right here is an antiderivative of x cubed. Because if you take the derivative of that, you get this, right? This is called the general antiderivative of x cubed. Right? This is a specific, this is an antiderivative. It is a specific one, but it's not the only one. This is the general antiderivative of x cubed. Got it? Let's try something else. Now, do not tell me that it's 1/2 root x. Wrong way. We're going backwards now. Okay? We're going the other way. So when we were doing derivatives and we had radicals, didn't we like to turn them into rational exponents instead? Same thing's going to happen here with antiderivatives. Let's try and figure out what this is as rational exponents. That's what we got, right? And then tell me about the power on the antiderivative of this. What is the power going to have to be? One more than that power, right? So add 1 to this. 1/2 plus 1 is 3/2. So I know this much. I'm going to leave myself some space in the front here. I know this must be 3/2, right? What about the 5 in front? That constant just seems like it doesn't belong there, right? Just kind of throwing things off a little bit. When you take derivatives and constants are attached to the front, don't they come along for the ride? So if you go backwards, they're going to go along for the ride also. So I'd like us to place a 5 right here. Okay, that's our constant, but I still left a little space in there for a reason. Right now, if I took the derivative of this, this would come out, right? Hit this and become 15 halves. I don't want that. I want that 5 to just be left alone, right? I just want it to be a 5. So what I need to do is make this come out and become a 1 and leave the 5 alone. So what can I put out here? The reciprocal of this number. The reciprocal of that number is what? 2/3? Maybe I should have written that out. A little more space. I forgot to put plus c in there. Plus c. Does it make sense that this would work? Take the derivative of this. Really, you can ignore that. This will come down, hit that. That'll become a 1. Subtract 1 from that, it'll become 1/2. And the 5 will just come along. Got it? But let's actually put that together. What is that? 10/3. X to the 3 halves plus c. Now you can verify it for yourself. If you multiply that, you get 30/6, which is 5, and it works. It's a little more thinking involved there, right? Okay, let's try something else. How about -3 over the 5th root of x? What's the antiderivative of this? Okay, first rewrite it with rational exponents. This is -3 over x to what power? 1/5. But that can be rewritten as -3 x to the -1/5. Hey, wait a minute. Do you think, just what does your gut tell you? When I was back here, could I just take the antiderivative of each one of these separately? What do you think? If I asked you to take the derivative of that, would you do that? No. Because we have a quotient rule, don't we, for derivatives? Same thing going backwards. When you're doing an antiderivative of a quotient, you cannot just do them separately. So the only thing we can do at this point is rewrite this as a power. And now let's just use the same logic that we've been using. I know that my function f is going to have some stuff in front of it. The x is going to be to what power? 4/5. You're going to add 1 to this, okay? -1/5, add 1 is 4/5. I'm also going to want that 4/5 to go away when I bring it out. So the reciprocal, we'll always use the reciprocal, in fact. I put a 5/4 in front of that. And then what was the number in front that I wanted to come along for the ride? -3. Y'all see how that all worked? Let's put it together now. This is going to be -15/4 x to the 4/5 plus c. Forgot my plus c. The good news is that you can check your answer by taking the derivative, right? If you take derivative of this, you better get back that. So bring that out, and that would give you -3. Subtract 1 from that, you get -1/5. Boom, you're good. Questions? Okay, what about this one? Good. ln x, natural log of x. That is because you remember, right? You recognize that that's the derivative.